the answer videos. Shame on them. So just a reminder, test is on Thursday. I don't even have any odd blocks. I should mark out the Wednesday column, avoid my own confusion here. So in person or online, the test will be Thursday over day 1, day 2, day 3. So over the packet that you have, so we even planned ahead this time. You don't have to rip off to turn in. Like you've got days 1 through and 3. You'll turn those in on Thursday, and then we'll test, and then we'll do a little bit of new stuff after the test, because I don't think the test is going to take the whole time. All right, notes for day 3. You've got notes, so let's do a little fill-in-the-blank work here. All right, the argument of a log must always be positive. Do you know what the argument of a log is referring to? It's a word we don't. What's a word you may? It's a word you know, but maybe not in a math context. The argument is what you're taking the log of. And so we also use the word for the argument of a sine function, means what you're taking the sine of. The argument of a square root function is what you're taking the square root of. The argument of a log is what you're taking the log of. Must be positive, so whatever's in there must be greater than 0. Not equal to 0, greater than 0. This will matter more when we do equations, because sometimes we'll get extraneous solutions that don't really work, but save that for later. For now, what's inside has to be greater than 0. For us, today, that's going to lead to domain issues, like what can x be? Well, there can't be anything that makes that 0 or negative. Property number 2. If the base of the log matches its argument, the value of the function is 1. That sounds fancy, but if you remember the fishhook rule for exponents and logs, does that look familiar? You start at the base, loop around. Uh-oh, give me a yes or a no. Okay. That's how you change exponents to logs and logs to exponents. And we will definitely do more of that later. But that's why that works.
So is it 1 to the third power?
It's 3 to the first is 3.
Just long where you have to do that swap thing.
4 to the first is 4. 5 to the first is 1. And so let's say I ask you a really hard question like the log base 7.32 of 7.32.
1.
That would be 1. So it looks really weird, but that just means 7.3 to 1 equals 7.32.
And it's like for an equation, it's going to give us log of 7.32, and then 7.32 equals.
So we're kind of building up to be able to use this when we graph. We're going to pick what that is to make it work in a minute. Like in exponents, we pick the x's to be negative to make the exponents work. Here we're going to pick the x's to make the argument work for us. And by work, I mean give us easy answers. All right, if the log's argument is 1, the value of the function is 0. Because anything to the 0 is 1. 4 to the 0 is 1. 5 to the 0 is 1. So let's work with that tricky log base 7.32. What's log base 7.32 of 1? 0, because 7.32 to the 0 is 1. So you kind of put 2 and 3 together and you get the idea that we're going to make, we want to make the argument equal the base, because that makes an easy log problem. And we want to make the argument equal 1, because that makes the log problem an easy problem. So instead of working a bunch of hard log problems, we're going to work easy problems. We're going to force ourselves into easy problems by making the argument equal the base and the argument equal 1. Again, the parallel thing with the exponents was we wanted the exponent to be -1, 0, and 1 because that made the problem easy. Here we want the argument to be the base, and we want the argument to be 1 because that's going to make the problem easy. Number 4, some E stuff. Log base E is the same thing as natural log. Log base E is the exact same thing as natural log. E is a very common number in mathematics and in nature, and so because it showed up a lot, here's the sort of the history of it. This guy, I'm not sure how to say that name. I don't know if he went by Leonard or Leo or Leonard. His last name is Euler, like the old Houston Oilers. I know it looks like Euler, but it's really Euler. And so he discovered this number. And so, hey, if you discover the number, you get to name it. So that's why it's called E, because Mr. Euler wanted to use his name. And hey, rightly so. The further you go into math, well, you guys know that already. There's Avogadro's number and Planck's number and all that other stuff. You discover it, you name it. So Euler named it E.
I've never figured out the last number.
And yes, he died trying to figure out the last number of E. This is not really necessary for us. This is sort of a calculus thing. The definition of E. That's way more than. Save that for calculus. So that's sort of a side note, but we're not going to ask you a question about limits, and we're not going to ask you, take off for spelling Mr. Euler's first name, that sort of stuff. That's kind of just a side note. It is important to know that it's kind of like pi, and this is what you were joking about. Like there is no last digit of pi, there is no last digit of E. It's irrational. It goes on forever. And Mr. Conley has a contest of who can memorize the most digits of E or pi. It's because they're kind of the same type of number. They're both irrational. All right, graphing these things. Basically, the two rules for graphing. Well, there's probably more than that, but we want the argument to equal the base, and we want the argument to equal 1. Because, man, that's going to make our life easy. And sometimes, if x is the argument, then this is pretty easy. So if I want the argument to equal the base, what should I let x be for this problem? 4. The argument is 4. Argument equals base. Argument equals 1. And I pick 4 because what's log base 4 of 4? 1. And if I want the argument to be 1, well then x would be 1. And what's the log of 1? Doesn't matter what the base is. 0. Okay, this is only 2 points. So let's graph these 2 points and then we'll figure out what else is going on here. So 4, 1. And 4, 1 and 1, 0. And you know what? Let's make it 3 rules. Argument equals base. Argument equals 1. Domain. Well, argument has to be greater than 0. So that means for this problem, x has to be greater than 0. So it's almost like I'd like to put a line right there to say, hey, don't go past this line. That's a barrier. That's a wall. Build the wall. Don't cross the wall. Get into an immigration debate here. Don't want to do that. But what does that look like in terms of what's a math word? I don't want a politics word. I want a math word. That's an asymptote. And so that 2 points with an asymptote, maybe that's enough to figure out what this thing looks like. All right, number 2. I want the argument to equal the base. I want the argument to equal 1. And I need the argument to be greater than 0. That'll be it'll give me 2 points and 1 asymptote. So if I want the argument to equal the base, although, be careful, look at the difference between 2 and 3 right here. On number 3, the argument is x plus 3. On number 2, what's the argument? Just x. If we're thinking parent function, which is the other way to work these, what's the plus 3 do at the end to the graph? It makes it go up 3. Alright, if I want the argument to equal the base, that means we should put 4 there. And then we'd have log base 4 of 4, which is 1. And 1 plus 3 is 4. If I want the argument to equal 1, then I'll put 1 in there. And that means log of 1 is 0, but 0 plus 3 is 3. And the argument has to be greater than 0. So that means, again, I've got the wall at 0. One comma 3. 4 comma 4. Not much to go on, but the asymptote there is helpful. Yes, David.
Is the asymptote never not going to be 0?
The asymptote is the asymptote never not going to be 0? Let me ask. Can I rephrase your question to? Is the asymptote always going to be 0? No, it is not. And I'll show you in just a minute. By the way, think about parent functions and compare number 1 and number 2. We said we wanted to go up 3. Look what happened to the y values from number 1 to number 2. What happened? It went up 3. So if you want to go parent function style on these, you could go back to the original one. Up 3 means add 3 to the y values, and there's your new graph. So, again, 2 ways to work these. Number 3. 3 rules. I want the argument to be the base. I want the argument to be 1. And I need the argument to be greater than 0. Okay, this one's going to require a little bit more thinking here. If I want the argument to equal the base, what does x need to be so that the argument equals the base? 1. And then log base 4 of 4 is 1. That's why we picked that. If I want the argument to be 1, x needs to be negative 2. And the log of 1 is 0.
How many points do we need?
Just 2, as long as you have the asymptote on there.
So you want to draw the asymptote?
negative 2, 0. Yes, because that's my third step. The argument is greater than 0. So that means x plus 3 is greater than 0. X needs to be greater than negative 3. So I've got my wall at negative 3. All right, parent function experts, which by the way is all of you. How does this graph differ from the parent function?
That one is left 3.
So which coordinate would change if we're going left?
X.
So now compare the x coordinates. We went left 3 to get there. So again, you can use parent function stuff that you know really well, or you can use the 3 argument rules. Argument's base, argument's 1, argument is greater than 0. Yes, question.
I don't understand why the asymptote couldn't change.
That's a really good question. So the asymptote, let me talk about number 3 and then we'll back up to number 2. So on number 3, we shifted everything to the left 3. So the asymptote went from x equals 0 to x equals 3. From 1 to 2, we shifted everything up 3. Well, the asymptote was up and down, so if I shifted up, it didn't really go anywhere. So you're right, it didn't go anywhere. Although I guess you could say, no, it did go somewhere. It moved up 3. You just can't tell that we moved it up 3. So good question on the asymptote changing. Number 4. 3 rules. Maybe you're tired of writing them down, but I want to emphasize it. Yes, Haven.
Can you go back to number 3?
Sure. So I want the argument to equal the base. So I was running out of room here. If I want the argument to equal the base, that means I want x plus 3 to be 4. Step 1. Make the argument equal the base. So that means x should be 1.
So if on the test we've already done the parent function, I can just use the x values and just subtract 3 from each one?
Correct. If you've done the parent function, then you don't really need to do those. You can just say, well, I'm going to go left 3, so I'm going to take my x values and subtract 3 from each of them and come up with it that way. And be careful with the asymptote, because you need to move the asymptote left 3 as well. Although if you didn't move the asymptote and you had those 2 points, surely you would realize that does not look right. Number 4. 3 rules. Argument equals base. Argument equals 1. Argument has to be greater than 0. Again, you can use the parent function rules, but you still have to know these 3 rules to graph the first one, so that's why we're going to graph them that way. Alright, if I want the argument to equal the base, what does x need to be? Negative 4. And then log base 4 of 4 is 1. If I want the argument to equal 1, what does x need to be? Negative 1. And the log of 1 is 0. So negative 4, 1. Negative 1, 0. And the argument has to be greater than 0. Ooh, this is a fun rule that we haven't done in forever. What do I need to do to get x by itself? Divide by negative 1. And when we divide by a negative, flip that and x has to be less than 0. Which I guess makes sense if you look at the picture. You got points over there that are x is less than 0. Okay, parent function experts. What does a negative on the x do? Flips it. It's sort of an x flip. And sure enough, look at the points of number 4 compared to number 1, and there's an x flip. So you can accomplish the table with the parent function rules or the log rules. Or if you know both, you kind of do both to make sure it makes sense. Number 5. Oh, lovely. Natural log. What's the base of a natural log?
Just E.
E. And so some people, like nobody who's dealt with natural logs for more than a week will write that. But you guys haven't dealt with natural logs for more than a week. So if you want to write that as log base E, that is completely okay. It's completely accurate. Like mathematicians would look down on you and sneer at you and say, oh, that's so juvenile. But hey, if it helps you remember what's going on, it's absolutely correct. There's nothing wrong with it. So let's see. The rules are, I want the argument to equal the base. I want the argument to equal 1. And I need the argument to be greater than 0. Here we go. Made my notes line up better this time. So if I want the argument to equal the base, what should x be? E. And when I go to the graph, I know that's 2.7. Log base E of E is 1, because e to the 1 is E. If I want my argument to equal 1, well, that's just 1. And what's log base E of 1 is 0. And then I need x to be greater than 0. What did we say E was equal to? 2.7-ish. The risk of switching methods, on number 6, do you want me to use the log rules or do you want me to use the parent function rules? I mean, it doesn't matter. I'm going to get the same thing. Nobody voted. So I'm going to use the log rules because you've got to know the log rules to graph the first one. After that, then you can use parent function. But so you can't only know the parent function rules. You've got to know the log rules to get started. And the log rules are base 1 and 0. Argument equals base, argument equals 1, argument greater than 0. So negative E, negative 1, and x is less than 0. Let's see. Natural log of E is 1. Natural log of 1 is 0. So that's negative 2.7, comma 1. Negative 1, 0. X equals 0. Is there a question, gentlemen? Number 6? No, number 7. We're not to number 7 yet. Parent function experts, if we had done it that way, what's the negative in front of the x do? Flip it in x. And so sure enough, we could have just changed the value, changed the sign of the x's and come up with our table. Number 7. What's the negative out front going to do? I'm asking out of order here, but flip it up and down. Argument equals base equals 1 greater than 0. How's that for shorthand? So E1 and x has to be greater than 0. So the negative natural log of E, well, the natural log of E is 1, but then the negative on it.
Doesn't ln always have that little e there, no matter where it is? Or is that just...
What little e?
does
This
that-
e?
Yeah, there's natural...
Well, if you, the only other option, log base e.
Is it log when you don't have anything there as the lower exponent? It's going to be the...
If you don't have anything there, it's a 10. If it says log. Log of 1 is 0, negative 0 is still 0. 2.7, negative 1, 1, 0. X, or asymptote.
So the negative of ln doesn't travel to the x.
It goes out front. So you take the natural log of e and get 1 and then stick the negative on it.
I meant for deciding where the asymptote.
That negative doesn't matter to the asymptote at all, because the only thing that matters to the asymptote is the argument.
How do you know that one's going up?
How do I know that?
Like the other ones have been like facing down.
So this is where the parent function knowledge is helpful, right? Because we said that that's going to flip it. And so if you look at number 5 compared to number 7, they're flipped in the y direction. Let's pass on number 8, although just parent function wise, what's that going to do? Up 3. And so if you wanted to graph it parent function style, how would you change your parent function table of values? What would change about it? Add 3 to which one? X's or Y's? Y, because you're going up 3. So that's kind of a sneaky way to do it, is you got to have the first one, but after you have the first one, you can use the parent function stuff.
So for the ln one, we're just going to put that e for the first x.
Yep. I mean, that's the other way to do it, is forget the rules, just memorize the table, but that doesn't, I don't like that rule. I like knowing what's going on, not memorizing.
If it's a negative x, then if the front part would be negatives.
Like number 6.
Yeah.
Let's answer some questions on number 9. But we have the picture of natural logs, so the question should be easy. Might be too strong a word, but I can look at number 9 or number 5. See graph of number 5. What's the domain? 0 to infinity. And we don't include 0, because can't take the log of 0. How about the range, the y values?
Negative infinity to infinity.
Good. All real numbers. The asymptote, x equals 0. It's like we've already done all these. We're just now answering questions verbally, I guess. What are the x-intercepts? Careful, 1, 0, where it crosses the x-axis. What are the y-intercepts? None. Name 2 points. Well, look at our table up there. E1 and 1, 0. So similar to yesterday, you get questions like this, either draw the graph or go find the graph, and then the questions are pretty easy. So on Thursday, do worksheets 1 through 3. And there is a test. over worksheets 1 through 3. Now, I suspect we'll take 5 or 10 minutes to answer questions from worksheet 3, since we won't have had a chance to do that yet. So, on Thursday, we'll do questions from worksheet 3, then we'll take the test, and then we'll do notes for the next day for worksheet 4.